In this video, we're going to consider the same problem of an oscillator chain and collective modes in the chain. But now we're going to study quantum collective modes or quantum phonons in a quantum oscillator chain. So this problem sounds very complicated because we're going to be dealing with an infinite number of quantum degrees of freedom now. But as we shall see, actually in the end of the day, the results are going to be very similar to those in the classical case. So namely, the spectrum of quantum phonons apart from the zero-point energy is going to be identical to the spectrum of classical phonons. Now, to solve the problem, first we need to define what we want. So let me consider a slightly simpler version of what we looked at in the previous video. Now I'm going to study an oscillator chain consisting of the same type of oscillators and same type of atoms. So I have here identical atoms with a mass m and identical oscillators, identical sort of springs. Now it's going to be quantum springs of sorts with a stiffness k. So this is the x coordinate. And the corresponding classical Hamiltonian associated with this oscillator chain is presented here. So we have a sum going over all these atoms. So n here is, so let's say this is going to be n equals 1, n equals 2, n equals 3. So it just labels the atoms. And x sub n is the position of the corresponding atom. Now this is of course the kinetic energy and this is the potential energy. So it's essentially the same Hamiltonian we had before, but now just for a single species of atoms if you want. Now, to go to quantum problem, we need to quantize this Hamiltonian. We need to make it quantum. So how do we do this? Well, it turns out that actually it's very easy to do so. So it's as easy as it was in the case of a single harmonic oscillator. So all we have to do is just to put heads on top of h, p, and x. So which means that we made these variables in the classical case into operators in the quantum problem. So for example, if we're working in a position space, so let's say p sub n is simply a derivative minus I h bar d over dxn. So it acts only on the nth coordinate of the nth oscillator. Now, these x and p, they satisfy the canonical commutation relations. So if they correspond to the same atom, so x, n, and pn, they commute to I h bar. If they correspond to a different atom, let's say if n is not equal to, well, let's say if we have x, n, and pm, so then it's going to be 0 if n is not equal to n. So we can sort of unify these commutation relations by writing a delta symbol here. So which means that it's equal to I h bar 1 if n equals to m and 0 otherwise. So this is what it means to quantize this Hamiltonian. So now the next step we're going to perform is we're going to use our definition of the creation and annihilation operators that were introduced in the solution of the single harmonic oscillator, and we're going to represent each coordinate xn and momentum pn through the corresponding creation and annihilation operators a and a dagger. So here at the same you can check, going back to the first segment of the lecture today, that as a matter of fact these are exactly the same definitions we used before, but now we just have this additional index n which refers to the atoms in this chain. And of course these creation and annihilation operators, they satisfy their own canonical commutation relations as here. So they commute with one another, their commutator is equal to 0 if they correspond to different atoms, and otherwise if they correspond to the same atom, a n commutator with a dagger n is equal to 1. So what we're going to do now, we're going to plug in this expression of x and p through a and a dagger into this Hamiltonian, and let me do that. So if we do so, the Hamiltonian takes this form, which actually appears to be a more complicated looking form since there are more terms here than we had before, but we are on our way to solving the problem. So the strategy for solving the problem would be actually different from the sort of typical solution in single particle quantum mechanics, where we're dealing with the Schrödinger equation and wave function. So here, of course, we still would like to solve the Schrödinger equation. We have in mind this Schrödinger equation, but we don't worry too much at this stage about the form of the wave functions. We just want to know the energies that are possible in this system. Just like in the previous video, we just worried about the spectrum of the dispersion relation of classical waves. So here we want to know the dispersion relations for quantum waves. So how do we do this? So in order to solve the problem here, instead of working with the wave functions, we're going to be working with the operators themselves. And we're going to try to transform the Hamiltonian into a new, simpler form. So that basically we're going to be looking for a new set of operators. We're going to go from the operators, let's say an and an dagger with all possible n's, to new operators, let me call it, let's say bq and bq dagger, such that the form of the Hamiltonian in terms of this new creation and annihilation operators is going to be much simpler than the form which is written here. So basically the challenge here is to find a linear transformation of the original operators into a new form such that the Hamiltonian, which looks simple, and that such that the solution to this Hamiltonian would be known. So this is a bit of a technical challenge and a technical exercise. So the first step in this exercise is just to write the Hamiltonian in terms of this a and a dagger as is. So we have to basically expand these brackets and calculate the square of these brackets, which leads to a rather lengthy expression as here. So I have omitted here an overall constant. There could be a constant which corresponds essentially to an energy shift. And also I have written it in a slightly more friendly form. Well, it's not as long as I could have written it because of this term, which corresponds to Hermitian conjugate. So basically I have these guys, so you can just work it out, and we can work it out as an exercise if you want. So and you will see that you have many terms, and each term here must be compensated with the Hermitian conjugate term somewhere else, because the Hamiltonian in the end of the day must be a Hermitian operator. So and in this case it simplifies our life a little bit, because we don't have to write two lengthy expressions, but still it looks pretty bad. So there are a lot of terms we don't want to see, so we don't know what the spectrum, what the solution of this Hamiltonian is. We see a bunch of these a and a daggers in various combinations, and we see also couplings between different sides, etc., etc. So in order to solve this Hamiltonian in the way I just described, that is to find new set of operators that simplifies form, so just like in the classical case, it's convenient to perform a Fourier transform. But now it's going to be a Fourier transform for the creation and annihilation operators themselves. So what we have here is a representation of the annihilation here and the creation operators in terms of some other operators, a sub q and a sub q dagger. So I use the same symbols, but this is really different operators. And so these a sub q are, in a sense, Fourier images of this a sub n. And so the two are related via this Fourier transform, which now is an integral going from minus pi to pi. So, it's not from minus infinity to plus infinity, because we have a periodic array of these oscillators, not a continuum of oscillators. So it's more like actually Fourier series rather than Fourier transform that we're using. In any case, I'll be using this symbol here, so integral with the subscript q to sort of label all the terms that I have here. And in these notations, for example, the Fourier transform of the creation operator is presented here. So it can be obtained from this one simply by conjugating both sides. So that's why I have a minus sign here as opposed to a plus sign here. So there are a couple of identities that I want to emphasize without deriving them. So the first one is the sum over all integers, basically over all the oscillators in our problem. And so n goes from 0, plus minus 1, plus minus 2, etc. So, and if I sum over all these n's, these exponentials will give rise to 2 pi times the delta function. And sort of the inverse identity to it, if I integrate the exponential from minus pi to pi, so then the right hand side is going to be a delta symbol. So this integral is equal to 0 if n is not equal to 0, and is equal to 1, well, in trivial way otherwise. I'm mentioning these identities because they're very useful in deriving a form of the Hamiltonian in the Q space from the Hamiltonian we derived in the previous slide in real space, which was dependent on the index n. And this derivation, which takes a little bit of time and effort, I will leave mostly to you, and this will be one of problems in your upcoming homework for self-assessment, and probably this is going to be the most complicated problem there. However, there is one important identity that I want to prove explicitly here, and this will be an identity involving a commutator of two Q-space operators. So again, our goal would be to rewrite the Hamiltonian in terms of this A sub q and A sub q dagger. And I refer to these guys as annihilation and creation operators, but I haven't proven that they are indeed such operators. So what does it mean for them to be creation annihilation operators? So it would mean that they satisfy certain type of commutation relations, similar to the canonical commutation relations we have discussed in the previous lecture. So and these commutation relations for the real space operators A sub n, let's say A sub m dagger, we know that this is delta symbol of n and m. So now we want to check what kind of commutation relations these guys satisfy, and in order for me to work out these commutation relations, I'm going to use an inverse Fourier transform. So let's say the first term in this commutation relation, A sub q1, can be written as a sum over n1 A sub n1 e to the power minus I q1 n1. So this is an inverse Fourier transform, in some sense opposite to this guy here. And the second term here is going to involve a sum, let's say, over n2 A dagger n2 e to the power plus I q2 n2. And this corresponds to the Fourier transform sort of reversing this relation. So now the commutator only cares about the operator. So and this is a linear operation. So we can factor out in some sense the sum, and we can factor out these exponentials. So and write this commutation relation as so. So it's going to be a sum over n1 and n2 e to the power I q2 n2 minus q1 n1. And here I'm going to have the commutator of A sub n1, A dagger sub n2. And so if we now compare this canonical commutation relation with this guy, we're going to see that this is nothing but the delta symbol of n1 and n2, which means that it sort of extracts just one term out of this sum, where n1 is equal to n2. And what we can do, we can simply set n1 equals to n2, and let's say we will set n1 equals n2 and equals to some other n. And so we're going to write it as follows. So it's going to be equal to the sum over n now, e to the power I q2 minus q1 times n. And that's it. So the operators are gone. And now at this stage, we're going to use finally this identity, the first identity that I just defined. And we'll write the final result. So let me actually write it in red. And it's going to be equal to 2 pi delta function of q1 minus q2, or q2 minus q1. So and this to be compared with this canonical commutation relation. So and as you can see, of course, here this is in some sense a continuum version of this canonical commutation relation. And this means actually that these guys, a sub q1, well, a sub q and a sub q dagger, they too represent annihilation and creation operators. But what do these creation and annihilation operators create or destroy? So unlike a sub n and a sub n dagger, which sort of create local oscillations of a particular site of a particular oscillator somewhere in a well-defined position in space, so these a sub q and a sub q dagger, they annihilate and create waves, if you want, propagating through the oscillator chain. So these guys are not local in space. They instead create waves with a certain wave vector, and q basically is the wave vector. So here again I'm using the units where the lengths are measured in the units of the oscillator length, so the distance between the neighboring equilibrium sides. But in any case, so this is really the interpretation of what we're doing. And now if we plug in this expression, these expressions into the Hamiltonian in the previous slide, and use these identities and other simple algebraic manipulations, we're going to arrive at the following expression for the same Hamiltonian. So this is the very same Hamiltonian we started with, but now rewritten in terms of this a sub q and a sub q dagger. And well, it's not at all obvious that this is a result, and well, this capital A and capital B, these coefficients here have this form, and it's not obvious at all. So this actually, to derive this guy would be a challenge for you in the bonus problem of your homework here.